why do we want basis? Because it allows us to represent anything in this set as a linear combination of these three vectors uniquely. So it's a non-redundant list. Okay. Being linearly independent means that you can't reduce by more. It has to be 3. So as a bonus, we know that the vector space, this vector space is dimension 3 because this list has length 3. Okay. The problem is that not all vector spaces come with a naturally equipped basis. And this is usually the case. There are many places where you use linear algebra. The two most prevalent ones are when you solve differential equations, especially when you're trying to solve differential equations numerically. You use a lot of linear algebra. And also when you try to do differential geometry, which is like things about curved spaces. And if you have curved spaces, you have like tangent spaces at each point, and those are separate vector spaces. All these cases, you don't have a naturally equipped basis for it, and you end up having to worry about what's the basis, and then another question that naturally arises is like, are they orthogonal? And in most cases, they're not. Okay? They're not orthogonal. Are they normalized? Meaning that are they unit vectors? And the answer is no. See, the ideal thing that you would like to have is something called orthonormal basis, which means all of these basis vectors are orthogonal to each other, and also their sizes are 1. So that would be nice, but in most cases, if you just choose whatever that works, their angles are orthogonal, and their sizes are not 1. But then, what do you mean by the angles between these two vectors? That makes no sense because these are not geometrical vectors that we know of, right? These are abstract vectors, right? So when you try to talk about angles between vectors, then you realize, well, the only way you can make sense of angles between vectors is if you have an inner product. Okay? Only when you have an inner product you can talk about angles between vectors. Now, there's a problem with inner product in function spaces as well. See, the regular inner product is what? You just take component-wise multiplication and you add, right? But then, what do you mean by that here? It's a bit strange, right? So let me first write down one inner product that usually is chosen for function spaces, and then let's try to talk about how to normalize or find angles or stuff like that. Okay? So let me pose a question. Define inner product of two vectors in this space U, so that the vectors here are really functions or polynomials, as integral of px times qx times dx, and we'll integrate from 0 to 1. And I just chose 0 and 1 because that's the most convenient one. I could have chosen something else. Okay? Now, do you remember the properties of the inner product that we talked about? The first one was that it has to be linear in the first component, right? And second is that we can switch the two things around, right? So it's symmetric. And then,
positive oh, that's for the Hermitian.
No, it's for both. And then you also need positive definite.
Yeah, positive definite.
Now, if it's linear in the first component and then you can also swap, that means the second component should also be linear as well. So an inner product, in a shorthand, people just say this is a symmetric bilinear form. Bilinear means it's linear here and linear here. Okay? It's a symmetric bilinear form, which is also positive definite. Or people just say, here's a positive definite symmetric bilinear form. That's a long word, but that's another way to say what an inner product is. Okay? So let's say we have a symmetric positive definite, positive definite symmetric bilinear form. Okay? And we, let's say, we define this as that. Now, can you see that this is indeed symmetric, right? Px times qx, qx times px doesn't matter, right? Do you also see that if it's px, it can never be 0. It always has to be positive, unless px itself is 0. You put any non-zero function here, px times px will give you some positive valued function. So if you integrate, it will be a positive value, right? So px will give you some positive value here. And then thirdly, being linear is kind of easy to see because, well, it's hard, cumbersome to write down, but it's kind of straightforward. You just replace px by, say, a times fx plus g, a times f of x plus b times gx. You plug it in here, and then you can expand the integration because integration itself is linear. Right? So it's going to be linear with respect to p, and then linear with respect to q. So this is going to satisfy all the properties of being an inner product. Okay? Which means it actually should have a basis where if you choose the right basis, then under that basis, this inner product will take the form of the identity, which simply means that in that basis, it looks like the regular inner product that we know of. Okay? There should be a basis. Yes?
So if it wasn't an inner product, you couldn't take the integral of it. It's what we're doing now, right?
No. Px is a polynomial, qx is a polynomial. We can always take integrals of polynomials. Yeah. What I'm trying to say is that if you define a function like this, a function from two polynomials to a single number like this, then you can check the three properties of being an inner product, which are symmetric bilinear and then positive definite. You can check that all three are true, so you can very well say that this is an inner product in this space.
So why do we put the integral then?
If you don't have the integral, then what can you do?
Oh, okay. Oh, in the space. Okay.
I need a number.
Right.
Yeah.
Okay.
Well, okay. So here's something you could try, which is like, say, p of 1 times q of 1. That's a nice exercise. So here's a question. If I define px, qx like that, is that an inner product? First, is it symmetric?
Yes.
Is it bilinear?
Yes.
Yes, it is, because if you have like a times f of 1 plus b times g of 1 plugged into p1, right? Then you can just distribute it and say this is a times f1 q1 plus b times g1 q1, right? And this side would be a times f plus bg times q, right? And this side would be a times fg plus b times fq, b times gq, right? So of course it's linear. So it's linear and symmetric. Is it positive definite?
Yes.
No. That's where it fails. Why? Because if for positive definite you need to say px should give you a number that's always positive except for 0, right? When does it fail?
Oh, if it's negative.
No, negative times negative is positive. That's not the problem. The problem is, you can have a polynomial whose value at 1 is 0. Right? The value at 1 could be 0. And in that case, this is not going to give you a positive definiteness. Right? Let me see, maybe. Yeah, so for example, let me see. Yeah, so if you have this polynomial, if you plug in 1, you get 0, right? But if you plug in p prime of 1, you also get 0. Right? If you differentiate this as x minus 1, so it still satisfies this, right? But then, for this polynomial, if you plug it into here, what happens? P1 is 0, P1 is 0, so you get equal to 0, even though the original polynomial is non-zero. So it will violate the requirement that your inner product has to be positive definite. Does that make sense? Right. So this wouldn't be a inner product. So that's a nice exercise to try. You can try other kinds of inner products.
So the inner product is like, so you did P of 1 and Q of 1, right? And you said if any polynomial does not satisfy the positive definite.
Not polynomial, inner product. If any inner product.
Yeah.
So we're trying to okay. So all right. Any function that has 2 arguments. Okay. Just give me any function with 2 arguments, and then now you check 3 requirements: bilinear, symmetric, positive definite. If any one of them is violated, then you can't call this an inner product. But if all 3 are true, then now you can call this as inner product. But then that seems still so arbitrary, right? You feel like there should be just one inner product. Why are you saying that anything that satisfies all 3 should be called inner product? Well, it just means that once you have an inner product, you have a nice way to measure stuff. Okay? You can measure things. Distances are measured by what? If you have 2 points in a vector space, you just take the difference of the 2 to make a new vector space, a new vector by taking this minus this, right? You get this vector, and then measuring the size using your inner product will give you the distance between the 2 points, right? So having inner product gives you distances inside your vector space. And also because inner product is the norm of one vector times norm of another vector times cosine of the angle between, now you can measure angles between the vectors. So once you have the inner product, you can do all kinds of things. You can measure distances, you can measure angles. You can talk about which is further away, which is closer, and that allows you to do many things. Like for example, in machine learning, you probably learned k nearest neighbors, right? So in that method, you also have, Euclidean metric is not the only way. There are other kinds of metrics that you can use to measure distances, right? So if you use some kind of a new inner product, you have different notion of a distance. Okay? And depending on which one you use, maybe it's more efficient. Some inner products will be harder to calculate. Some might be easier. That's what I'm saying. Okay? So see, since there is no God-given basis for some vector space, right? then you don't have a God-given inner product. You're given you're presented with some vector space, and all you know is that it's a vector space. Now you have to invent a whole lot of stuff if you want to do things in it. Okay? So you're just coming up with basis for this space, and now you come up with possible inner product, and now you want to think about what to do with that basis. Is that okay?